we're getting into different strategies involving integration just because we've learned all these individual skills, but now it's time to start thinking about how we can distinguish one method from another. And a lot of it has to do with experience, but sometimes you can notice some similar characteristics. So I like to start off with this set of examples because they're very similar, but they involve much different ways of going about things. The first one's actually very easy because that's a rule. And we've talked about this a few times. We know that the antiderivative of du over 1 plus u squared is the arctan or inverse tangent of u plus c. All right, so this one is just the inverse tangent of x plus c. All right, so that's nice and easy. All right, but you can see the one below it, very similar structure, but vastly different because whenever I see a fraction, one of the things that I look for is whether the numerator, so is the numerator a derivative of the denominator. All right, so I don't want to leave it as, is it the derivative or is it a derivative? Is it a multiple of the derivative? All right, in this case, it happens to be exactly the derivative. So if I take the derivative of x squared plus 1, I get 2x. All right, so that's telling me, if you go based off of the rule, du over u is the natural log of u plus c, we would conclude that this is equal to the natural log of x squared plus 1 plus c. All right, so that one's not bad either. The last one, it has similar structure in terms of the x squared plus 1, but the top is not a derivative of the bottom, and also we're running into a little bit of a issue when it comes to rules, because it looks like x squared plus 1 looks like an inverse tangent, but it's not quite. So there's some nifty tricks that you can use, but there's also some old algebraic concepts that you can use. Like, for example, if you wanted to divide with long division. But one of the nifty tricks that you could use is sort of manufacture a relationship that might not necessarily be obvious. So I have an x squared plus 1. And I think to myself, it would be great if I could cancel out the x squared plus 1. So I'm going to add a 1 to the top. But I can't just do that. It's kind of like the idea of throwing a radical onto something. If I throw a radical on it, I have to square it to correct for that. So if I'm going to add a 1, I'm going to correct for that by subtracting a 1. All right? That allows me to split the fraction into two parts. Because if there's a numerator that contains addition and subtraction, it can be split. I choose to split it this way. X squared plus 1 over x squared plus 1 minus 1 over x squared plus 1 dx. So, in doing so, I have two separate integrals that I can work off of. Probably could have rewrote it in less time, but as you know, this is one of my things. So anything over itself is 1. Antiderivative of 1 with respect to x is just an x, so I'd have x minus, and this is a rule, this is the arctangent or inverse tangent of x plus c. Alright, so the similar structure actually kind of brings you back to something familiar, but not maybe in a way that you might have expected.